So welcome everyone to the Tuesday seminar. It's my job to introduce Stefan. The first speaker is a graduate student in my lab. He's in his 4th year. He's been interested in search algorithms in ants. So how ants can cover a large space and deal with various trade-offs during the phase where they're exploring or finding resources. He's done a lot of animal tracking, video tracking, and analyzing two-dimensional paths. But today he's going to talk about, I think, the role of models. I don't have the title ready here, but Stefan probably has it on his first slide. So Stefan, go ahead. Inference for models. There we go.
I decided to switch it up a little bit today and not talk about my thesis and instead talk about a different topic that I currently feel strongly about. First of all, I want to give thanks to the Dornhaus Lab, who has been very influential in shaping up the presentation. So I will first give you a bit of a background info into why swarms might be really awesome, at least for the participants, and then I will talk about the scientific community, how it has tried to identify these cool dynamic structures, how they arise from individuals, and what we all can learn from this process for thinking about mechanistic models in general. So here's just a teaser about some of the benefits of swarms. So first of all, not all members of the group have to know about a good food source or a shelter or a predator or where to migrate to, because just about 5% of the swarm has to be informed to lead the rest of the group to the goal. And even when no one is really confident in their goal and there is also navigational noise, then being in a group still helps because of something called consensus decision making. That makes the group have more accurate and precise decisions because the noise is just averaged out. And of course, moving in a group also has energetic benefits. Because there is a reduction of turbulences, especially when you're moving quickly or through water. For example, one study found that fish need about 30% less energy when swimming behind another fish, but also 15% less when they're swimming in front of another fish. And by the way, this effect also applies to biking. So when somebody is drafting behind you, it also benefits you. However, the opposite is true for pigeons because they have to flap about 8 times more frequently when they're in a group in order to just follow those really quick movement decisions of their flock mates. So apparently the other benefits of the group are still worth it. So now I'll turn to the main part, which is taking you through a little journey of trying to figure out how these swarms can form from individuals using models. So the TLDR, or take home, of what I want to get across is that first, the purpose of most biological models is not to represent the real world most accurately, because that would be engineering. And instead, the purpose of most biological models is to gain insight into the real world. And in other words, that means that they are a means to an end or a tool and not an end in themselves. So that means that just a well-fitting model alone, that doesn't really tell us more than it is possibly a good representation of what might be going on. And second, in this sense, models are hypotheses, and we should also treat them like that. Because usually many mechanisms or models can lead to the same or a similar pattern, and we must explore these alternative models just as well, and then compare their predictions against each other and to the real world. So I am aware that this might seem like a lecture by somebody who is not the most qualified among us to talk about it, but I just found myself always making these mistakes about how to think about models properly, and I would just like to take the opportunity to share my view and hopefully also get some of your opinions on it. So the first model, recreating the swarm behavior from individual agents, it was done by Aoki in 1982. And he conceived that every agent or void has 3 zones around it. If another agent is in the widest zone of that focal agent, it gets attracted to it. And if it gets too close, it is repulsed by it. And if the other agent is in between those two zones, then the focal agent aligns with it. And if there are multiple agents in these zones, then these forces get linearly integrated, or they make a vector summation. And this model was then widely adopted because it is so simple and it can create different behaviors like swarming or loosely coherent groups, as you see here, and also highly parallelized groups, and all of that just by changing the different radii. And then naturally, people wanted to find out whether this model does fit also with the real world data. So instead of assigning some arbitrary numbers for the radii, they just got them from most fish and also some other select animals. They did this by first filming pairs and triplets of these animals, and then they measured these distances and headings from one frame of a video and compared that to the same measurements in the next frame. And then they fit the model with these radii that they got and checked whether similar group level behaviors of the model were actually consistent with the group behavior of the real animals. And lo and behold, yes, it fit really well. And you just have to make some slight modifications, such as oblong zones for fish and not circles. But it's also not true for other species. And some have more attraction and repulsion in the front and in their back, and instead more alignment to the sides. And this is, of course, not discrete, but it's more like a smooth function. And with all these modifications, the models then fit really well, as you can see in this plot here. And with newer techniques such as deep neural networks, we can, of course, get much more data and parameterize the model even better. So now we pretty much understand how these groups do what they do. And what we have learned mainly is that you can build a simple model that describes the group patterns quite well. So we have actually gained some insight. But I would argue now that this insight is pretty weak and that it doesn't tell us too much about what is going on in the real world, or at least we can't be too confident about it. Because to recap, the whole process was essentially like, we asked how can animals stay in certain distances to one another and be aligned so well? And then we built a model with increasing realism in which those exact things were explicitly encoded. And then we checked again whether this model, just with a few more agents, represents the real world. In an analogy, I find this similar to asking, how can celestial objects move across the sky in this pattern? And we came up in the past with a simple model, and then with more and more data, it got more realistic, and it could recreate the pattern that we see. But of course, now we know that there is another model on the block, which is not as intuitive as the classic model, but describes the real world just as good. And it is even simpler. So now the question becomes, are there these heliocentric models for collective movement? So this leads me to the bottom half of the take home. We have now worked on one hypothesis out of the many, which could also explain the pattern that we just don't know about. And since we can only gain confidence in a hypothesis by rejecting alternative hypotheses, we must identify them and then check how much better our model explains the pattern than the other models and in which ways. So how do we now come up with new hypotheses at the forefront of science? Well, mainly through natural history observation and exploratory research, also taking inspiration from other fields of research, and by testing the assumptions of our models explicitly, because they can be seen as kind of like sub-hypotheses in themselves. So that's pretty much what collective movement researchers afterwards also did. And the first assumption I will go over is that individuals react to everyone in their zones, which might not be true. So as an example, when starlings are attacked by a predator, just like here, a hawk, they stay much closer together than the classical model would predict. And another model where these birds were only attending to about 6 to 7 of their neighbors, that fit the data much better. And a later model also showed that attending to more than 7 neighbors does not really increase that navigational precision that I was talking about earlier. And another way of selecting your interaction partners is taking the first shell of the Voronoi tessellation, which is illustrated here in orange, and data from flagtails, these fish here. This also fits better to this model than the classical radius model or the k-nearest neighbor model. But it is still closest what we see to a k-nearest neighbor model of 6 to 8 influential neighbors, just like with the starlings. And maybe we can use the different predictions that these models make to systematically test against the real systems. Another model that is not yet based on data showed us that when an agent interacts with anyone it can see, that can also reproduce a swarming behavior. And so interestingly, smaller groups with that model resemble more the radius model, while larger groups resemble more the k-nearest neighbor models. So we have now seen that all these 3 different models can create some swarm behavior, and in some cases even exactly the same behavior. The next assumption is that animals in a swarm react to individuals. So recently there have been some papers that came out that suggest that individuals might react to some other feature of the group, not the individuals. And my hunch is that this might be also a little bit closer to what's actually going on in the minds of these animals when they react to their swarm. So the first model here uses also the visual field of agents. And here they are attracted to edges in their visual field and repelled by solid areas in the visual field. As you can see in these plots, they also form swarms which resemble many different group behaviors that we see in nature. And you can create all these different behaviors by just changing 2 variables in this quite simple decision function. This next model also uses the visual field. And here every agent makes a prediction at every time step that goes like this. If all others keep their velocity, which move gives me the highest number of different visual patterns in the following time step? So this is also pretty much equal to the position where the agent has the most movement options in the future. And in this case, it would be the middle one. The farther the agents can predict the future, the larger the groups can also be before they break down. And in this one as well, you see pretty interesting murmuration emerging as well without any radii or any interactions with individuals. So pretty radically different than the classic model. Then we also have some support, at least from empirical data, that at least in some animal species, they might not be interacting with individuals, but with some other features of the group. And the study has found that in these midges here, they are repelled only by their nearest neighbor that you see in dark red here, but that you could not discern whether they are attracted to the neighbors or attracted to the empty space between the swarm or to the swarm center. And you can see that all those lines lie on top of one another, so this is why we can't really discern them. So to check whether these midges could potentially use the radius model, the authors also parameterized that with the midge data and did the same analysis on it that they did with the real midges. And we clearly see that this plot does not look like the graphs on the left side. So there is probably a different behavioral model going on inside the midges. If you remember that slide, we saw a pretty good fit between the experiment and simulation, but what if fairly different models also fit the data, or maybe even better? So for the remainder, I will just showcase some experimental studies, which could be very informative I think, about which model assumptions are met with which species and which model is true in which species. So first, I'm going to take a look at the sensory abilities of fish. So when safe are blinded, these fish here, they swim farther apart from one another than usual. And when their lateral line is sectioned, they swim closer together and more side by side than usual. And I believe that experiments like these can give us an opportunity to estimate the individual contributions of those different sensory and maybe also cognitive factors which can make these animals behave in such a group manner. Another study like this, here the authors also got really precise data on the visual field of these two fish through experiments and dissection, and then they derived predictions for a predator avoidance behavior, the group shape in total, and the distances to every fish's nearest neighbor. And as far as I know, those predictions have not been tested yet. Another, I believe, very promising approach is to try our models in the real world here using robots. So this is showing an open loop system where the robot, which is slightly bigger than the other fish, is swimming in a zigzag manner, and it's open loop because it does not react to the behaviors of the other fish. But the true power really lies in closed loop systems, where this robot also reacts to the other fish and adjusts its movement. So in these models, I think it is really powerful to just implement those robots with different behaviors, different models, and then check how similar they are to only fish swarms. And finally, we can also elucidate how behaviors are linked evolutionarily and maybe traded off through artificial selection experiments. So here in just 3 generations, those guppies were selected for more alignment, and which you can see in the right video. And these groups also show more cohesion, and they choose to swim faster, especially when they're in groups. And I really think this is a cool experiment and didn't just include it to satisfy the evolutionary people among us. So now we are at the place where this kind of slide usually sits, and I will just reiterate that we mostly want to learn about the world as scientists rather than to recreate it. And the best way of doing so is to see where and in which way you're wrong. And in order to facilitate that learning and knowing in which way you're wrong, we must compare the predictions of different hypotheses, which in this case are models. And a good way of generating competing hypotheses is, for example, to check assumptions explicitly and also be creative about what other hypotheses and models might be out there. And with that, I will take any questions or answer discussion points. Thanks.
Looks like there's a question from Rick Michaud in the chat.
Okay, I find this very interesting. Thank you. You're welcome. It was surprising to me that the models of swarming you discussed consider how to create swarms without discussing ideas of the function of the swarm. Yes, you did not miss anything. If not, what about including hypotheses about function of swarm? Well, I was just, so basically the assumption of this talk was to just focus on how they are created. So the mechanism or the proximate side of this whole system. And there are separate hypotheses that about the functions of the swarm. So something that I briefly just touched on in the beginning, there are many hypotheses about predator avoidance, for example, many eyes and predator confusion hypotheses. And I did not go that deep into the literature yet. Yes, it's of course the distinction between why and how. And I would love to give another talk about the functions of the swarm, but that was just a deliberate decision.
How about building models that include both? Are people doing that, or are you doing that?
Oh, models, okay. I am not doing that. How would that work? So I could imagine like an evolutionary algorithm that selects different swarm mechanisms. That might be something one could do. But what would be the purpose of this model?
Well, to more accurately predict the world and understand it deeper, right? So the same as yours, but I mean, both are important, like I say in the comment, mechanism and function. But like a full explanation is usually both, and so I'm just surprised that they're so cleanly separated in this area of work.
Yes, my guess is that they are not really combined yet, because both models or hypotheses are kind of difficult in themselves. So it would be making a really complicated, a really complex model or sets of models to combine those. But I agree there would be something really powerful potentially.
I think it would be really interesting just to add to that comment. I think it would be really interesting to study whether if you have swarms that have different functions, that their optimal mechanisms would be different. So in other words, if the function affects which of the different potential mechanisms for creating cohesion or whatever so I missed the beginning of my sentence. So the point is, if in different animals, there could be swarms that fulfill different functions, and it may be that those different functions create different selection pressures for different mechanisms. So in other words, that function determines or affects optimal mechanism. But I think here, the point for the fish that Stefan was saying is that the point of the model is to test which mechanism they're actually using. And in order to test which mechanism they're actually using, you have to compare different models, or you have to have different hypotheses to begin with about what mechanism they may be using. And it's not enough to just basically formalize one, fit it to the existing parameters, and then say that it works. So his point, I think, is about, regardless of what question you're trying to answer, whether it's about function or mechanism, you have to actually compare the different alternatives, and you can't just fit one model to your system.
And I certainly agree with that. I think it was a great presentation. I really enjoyed it. I hope my comment didn't indicate otherwise.
Oh, no, thank you. Thank you for those questions. Stefan, there was actually a question from Chinmay at the very beginning also.
Yes. Okay, so does a model create an exaggerated version of the reality or a simplified version? So it must create a simplified version because it's not really possible to make something more complicated than reality. In reality, so it is exaggerated it must be exaggerated in some forms, but yeah, it's always simpler and as simple as we can handle it, basically. Another question. Other examples of multi-species swarms? And if so, would you expect the underlying swarm mechanisms and or functions to change? Yes, there are. I mean, you know, the ungulate, they aren't swarms, but ungulate are masses of animals. They are all multi-species. There are some fish and also some birds that are multi-species. And there's also a really interesting question, what kind of mechanisms they have and how they form together. I want to look into it. I'm not sure whether, so I don't think anyone has really looked closely at this, but it's really interesting whether there is maybe some coevolution between those different species going on, or whether this basic principle of how swarms could emerge is already like historically in very basal, and so they would just have to slightly evolve together. But yeah, it's an interesting thing to look at. Yeah. I'm interested to know if sensory perceptions, aside from visual retinal cues, to influence fish group swarm behavior. Stickleback literature seems to focus on individual vibrations. Yeah, so that's just the one slide or study that I presented on the lateral line. I missed to explain it that the lateral line is for short range perception of other individuals, mostly fish, through their kind of vibrations. It's just easiest to look at the visual fields. And we also have some data on others like electro sensory abilities, but it's still, there's too much to be looked at. So we have focused, or literature has focused on vision first.